this: V1 sin omega t plus V11 sin 11 omega t. Do you see actually any difference compared to earlier equations? So earlier you get third harmonic, but now your first harmonic appearing as the 11. By doing that, what you are actually achieving? Because this one will produce current of what magnitude? So I11 will be V11 divided by R square plus 11 omega L whole square, isn't it? So it will not have any impact. It will not have any impact because the impedance will be so high that it will not be able to produce any significant current.
What's the benefit of having very thickness pulses though? If you have a series of narrow pulses that are all the same width, then surely...
No, it's not same width. Actually, it will be slightly less and less and less.
Yes, I know. So why would we do that instead of pulse? So I would have thought that pulses are the same width, narrow pulses are the same width.
Ideally, basically, what actually you are trying to do, you are trying to make like that. So if you think of that, your area during this part is the maximum. So you are trying to replicating. So this position, your area is not much. Okay. So you are trying to replicating the sinusoidal wave. So this is the technique we use. So now, in terms of the analysis, you can actually do the analysis by Fourier, but if you think of that, I do not like to make this as a hardware. I do not like to make this as a hardware circuit. I am a software guy. Okay? I can actually make everything by software. You can do that by calculating. So this is your 0 degree, this is your 180 degree, this is your 360 degree. You know what will be my firing angle in terms of 0 to 180 degree, and I will get least amount of harmonic to make that happen. So it's possible by making software. So one of the problem for the software is that even though you say that angle remains same 360 degree for a period, but when you think of the frequency, it's 50 Hertz, your time period becomes 20 milliseconds. If you make it 40 Hertz, your time period becomes 25 milliseconds. So when you write that code in microcontroller, you cannot give the angle, you have to give the time. So making that time is a little bit difficult to make that. But earlier days, people used to use called table. So you take many tables, okay? So you design for each and every frequency, you store them, and you can use them. But then that does not give you the smooth frequency variation. So there are some advantages of the hardware. You can also do some parts using software, but still you will find that you cannot eliminate completely the hardware part. So this is the way we get using the PWM inverter. So this is all about single phase. So now I'll move to 3 phase because that's the most important thing for us. So what is the changes? What are the changes? So of course you can say that I want to make a 3 phase, so I can have 3 of them. 3 of them. So that means that you need 12 transistors. Okay? But in reality, you do not need 3 of this set. You just need another phase. Before I go to that, one more thing here is important is that while you design your control circuit for generating the pulse, the most important thing is that never ever give the pulse to 2 transistors in one leg simultaneously. Okay? You understand? Everyone understand that part? You cannot make T1 and T4 or T3 and T2 on at the same time. If you do that, what you are going to do? So what will happen? Your supply, see, always you have to think of that everybody likes to be at the state of minimum energy. Okay? That means we human beings are not grow up to take the challenge. So whenever is the easy thing, we try to get that. If there is easy way of making money, everybody will jump for that, isn't it? Everybody is same. Here in the electronic circuit, if you give an easy path, it will try to send the current, because the purpose of this supply is to send current. It will send the current. It will send all the current here, and what it does then? It will damage these transistors, isn't it? So this is one of the most important requirement for the control circuit. So who will design that? The control designer, whoever it is, needs to design that. I need to draw again. So that part is the most important part, that your circuit should not energize two transistors at the same leg at the same time. That is valid for the 3-phase too. So for 3-phase, we go 3 sets of leg. So this is my 3 sets of legs. They are all switch, semiconductor switch based on IGBT. Everybody has got the parallel, anti-parallel diode, no exception, because of the providing the path of the reverse current. So you got junction point. You got junction point here. So those junction points, 3 junction points, you connect to your load. So your load can be either it is star connected, or it can be either delta connected, because it's a 3-phase load. Okay, so either it is star or it's delta. It doesn't really matter how you got the load. What it matters is that 3-line terminal. So you connect them. So for delta it will be here. You connect them for star, and for, of course, not together star and delta, either of this. Okay. Now, one important thing we need to follow here is the naming of the transistor. We have 6 transistors. And we give name T1 to T6. T1 to T6. But what we do not give them arbitrary. There is a way of naming them. Okay, there is a way of naming them. So T1, T3, T5, T2, T4, T6. So it's not that T1, T4 this thing. So the reason of doing that, it helps for designing the control. Okay. Otherwise, you have to be careful while you are using the control circuit. So once you have that, so you can say this is my R, Y, P. So R, Y, P phase sequence. Okay. So I think you better not to have the delta there, so that don't get confused. So let us. It can be either star or delta, doesn't matter. Okay. So doesn't really matter whether it's a star or delta. So we take star connections so that we get okay, so this is your. Now in case of 3-phase, there are two types of modes for controlling the transistors. One is known as 180 degree conduction. Another is called 120 degree conduction. Of course, this is the crude. Again, I am talking about the crude, but actually you have to go for the PWM. So even within 180 degree, you will have lots of pulses. Now here, 180 degree conduction, what do we mean? We mean that once we fire a IGBT or fire a transistor, it will conduct for a period of 180 degree. Okay, it will conduct for a period of 180 degree. In case of 120 degree conductions, that time limited to 120 degree. Okay, that time limited to 120 degree. So either we conduct each transistor by 180 degree, or we allow each transistor to conduct 120 degree. So different way you can do that, but this is the main two methods for the firing of the transistor. Next important thing is that how do we actually give them the gate pulse? So here we have got the gate, so G1, G3, G5, G2, G6, G4. So we give them the gate pulse, at 60 degree interval. Okay, so think of that your period is 360 degree. Your period is 360 degree. You are actually giving the gate pulse from 1 to 6 for 60 degree. Okay, 60 degree interval. Okay, of course they are either 120 degree or 180 degree. So you start G1. After 60 degree, you give G2. After another 60 degree, you give G3. After another 60 degree, G4. Then G5. Then G6. Then you come back again to G1 and repeat the things. So that's the repetitive. So 60 degree is the delay. 60 degree is the delay for this numbering or the sequence, gate sequence. And for example, we go for 180 degree conductions. So then how do you actually see your sequence? So let us say okay, so 1, 2, 3, 4, 5, 6. So first is G1. I'm going for 180 degree conductions. So 180 degree conduction means, so this is your 0 degree, 60 degree, 120, 180, 240, 300, 360. Okay, and 360, of course, 360 means again 0, so 60. So I am giving 180 degree to G1. So that is my G1. So when I am giving the pulse, I am giving for a duration of 180 degree. Okay. Then I move to G2. So G2, I am giving a delay of 60 degree, but then again I am giving it for 180 degree. Then I am giving G3. So another delay of 60 degree. So that's my G3. Then G4. So G4, can you tell me what is the relationship between G1 and G4?
They cannot be on together.
They cannot be on together. So you see here, G1 was on, G4 was 0. When G1 goes to 0, G4 is on. Of course, ideally, this like that. But practically, between this and this, can you tell me what you should actually do? Between G1 and G4. G1 and G4. G1 is actually switching off. G4 is switching on. What do you actually do here? Practically what you must do.
Put a delay between at the same time, so they've got time for the current to dissipate.
Not exactly, but you need to give a delay. You understand? You need to give a delay because this one will not be switched off instantaneously when you take away the gate pulse. So you give a delay to ensure that G1 actually gone off. Then only you bring G4 on. So that's your G4, and then you get G5. So when you give G5, it's like this, but here it will be on, isn't it? And then you give G6, which will be so each one is delayed by 60 degree. So this is very easy to implement using some kind of counter. Okay, in hardware circuit, you actually call ring counter. So it's actually in a ring, but of course in microcontroller based circuit, you can just have a delay and then you call the delay every time. Same delay, you just switch it on in sequence. So at any instant, what is happening for your circuit here? At any instant, if you see how many devices will be on? 2 or 3?
3.
If you see between 0 to 60 degree, between 0 to 60 degree, G1, G5, G6, isn't it? So if I see in the diagram what I actually expect, I expect out of these 3, any 2 or 1 can be on, isn't it? Out of these top 3, either 1 or 2 can be on, because if all 3 on, you cannot actually switch on any bottom, isn't it? So either 1 or 2 can be on. If 1 is on, if you take out the bottom one of that same leg, other 2 can be on. So either T1 with T4, T2 or T6, or T3, T1 with T2. So that's the combination. Either 1 of top with 2 of bottom, or 2 of top with 1 of bottom, but you cannot have the 2 transistors from the same leg is on at the same time. So here what you can see, G1, G5 and G6. So if I take out G1, G5 and G6, you will have situation like that, isn't it? You will have the situation like this. So what you have here? So you will have a situation like that. So you can calculate what is the voltage appear across each winding and you can analyze. So I'm not going to do that, but it will be something like this. It will be something like this. So between 0 to 180 degree, you will see for VRN will be something like that. So this voltage will be roughly like Vs by 3. This will be 2 Vs by 3, Vs by 3, minus Vs by 3, minus 2 Vs by 3, minus Vs by 3, and so on. So even also in the crude method, you can see as if you are getting very nice sinusoidal. Okay, nice sinusoidal like that. But this is of course the crude way. Actually you do PWM. So in PWM, your voltage will come much higher fundamental component with very low harmonic component. And then of course this will be VRN, and VYN, it will be 120 degrees. So this is 60, this is 120, it will be starting like that here. So you start like this. So like this. So 120 degree phase shift. So this will be the waveform you will feed to the motor. So one thing you need to get that how do I actually do the V by F control? So I can control the frequency here. How do I control the voltage? So one of the things what most of the drive has got is the input circuit. So the input circuit, what you will have is so for example our Schneider drives, as you have noticed, I don't know whether you have noticed or not, it takes the power from single phase. Even there's a 3-phase drive, but it takes the power from single phase. So you may have the power from single phase. So what you got here in the inputs, so you will have so basically that is now going to the inverter. So here you will have the inverter. So this is your V input. If you have 3-phase input, then of course what you need here? If you have 3-phase input, you need another 2 diode, isn't it? So 3-phase rectifier. So if you have 3-phase, so you have got here 3-phase. So this is your 3-phase. Of course, you need to have the capacitor. So this capacitor holds the rectified voltage, but sometimes this does not give you, this does not give you any change of voltage. Okay, any change of voltage. So if you want to change the voltage and control that voltage, either you have to have a PWM DC to DC converter kind of things here. So where you can get the control voltage here, or sometimes you can make this diode as thyristor. But earlier days thyristor was quite popular, but here now you can make a DC-DC converter to make the variable voltage. Okay? So when you come across inverter, you will have the term either VSI or VFI. Another is CSI or CFI. So VSI stands for voltage source inverter. Okay, voltage source inverter. So the source is predominantly a voltage source. And F actually called voltage fade inverter. So some people, some book, you will get that term. And CSI is the current source inverter. And F for the fade. So voltage fade inverter or current fade inverter. So you can have either predominantly a voltage source or you can have predominantly a current source. Current source is, do you know the relationship between a voltage source and a current source?
One has fixed voltage and carries a current, one has fixed current, carries a voltage.
How do you do that? Suppose I give a voltage source. Can you make it a current source?
Yes.
How?
Thevenin to Norton.
Hmm?
You use a Thevenin equivalent and then convert to a Norton equivalent. So if you've got any circuit with voltage source and some resistors below in it, you can make a Thevenin approximation, and then the short circuit current in that approximation can be
Yeah. So so basically, I understand what you were talking about. But in practice, how do you actually do? So if you have a voltage source, so let us say you have a voltage source, and you want to make it a current source. So it's very simple way. You just add a very large value of inductor. Okay, so you just have a very large value of inductor. So predominantly that will make a current source. It's not a constant current source, but it's a current source. So the whole idea is that inductor will not allow the current to change quickly, so it can actually make as a current source. So usually the current source, you can make current source by using transistorized circuit. Okay, so voltage follower kind of circuit where the current is constant. But you can make for large current, you can make like that. So you can have either voltage source or current source, but most commonly used are the voltage source inverter. Okay? They are the most commonly used because the supply is the voltage for most of the cases.
Does that mean that you can have a current source inverter and turn it into a voltage source by having a really large capacitor?
Usually the other way around, no, because usually the sources are voltage source.
Okay, so you don't have to.
Yeah, so you don't get the current source as such. Okay, so most of the cases is a voltage source because your supply is voltage and you just rectify it, so you get the voltage source. But if your circuit demands a current source, you can make a current source. But usually you don't have the current source that you convert it to. You can do that, as you said, you can do that, but usually it is not the other way around. Okay, so what else I was planning to have here? So in case of 120 degree conductions, this width will be 120 degree. So that will make you only two devices, one from the top and one from the bottom will be conducting at the same time. So it's only two devices at the same time will conduct, and each one will conduct for 120 degree.
What's the trade-offs? What's the benefit of 120 versus
120
180?
you get actually less voltage in terms of the output RMS value, but it will actually give you much more simple control circuit because for 180 degree, as you can understand, that there is always a chance that two transistors the same leg because of so in 120 degree you can ensure that short circuit part can be fully eliminated because there is no way you have the two transistors coming at the same time. So that's what one of the advantage you have. But anyway, so this is not the actual circuit, because actual circuit will be PWM. So you've got a lot of pulses. So not a big pulse, but you will have a big pulse in the middle, and then you have got small pulses exactly the same way we have the for single phase. Any question?
Do we have to know how to design an inverter as an exam question, for example? Or do we just have to know?
I mean, of course, you have to know if you think after 1.5 years you got a job in a Sydney-based company, they decide to make inverter and they employ you, then of course you have to. But if you ask me whether for the test at this stage, so for designing of the inverter now, at least we are in a situation where most of them are like kind of standard. Okay, so you may not have the opportunity to design something new unless you come up with a completely different idea and you make the system more efficient. Okay, see, engineering systems, if you come up with a new idea with much more efficient, much smaller size, okay, much ease of operation, then you can always think of bringing something new.
So we just have to understand the principles of operation, not actually how to design them ourselves.
Yeah, I mean that's what I'm telling. That this is for your exam point of view, you don't need to worry too much. If you know this thing, it will be good enough. But for the design point of view, you need to know if you want to think of something, making something new. Okay? Okay, actually I will, so let us, so how do you actually get, so if you remember we started with the expression that Vt equal to A0 by 2 n omega t, okay? If your expression is like that, how do you actually get this A0, An and Bn? So A0 will be 1 by t, 0 to t, Bt, Tt. Or you can actually go for, if your period is pi, 2 pi, so 0 to 2 pi b theta d theta. Okay? That you get as the average value. What is your An? So that is 1 by t, 0 to t, Bt sine n omega t dt. us take one example. Let us take one example. So, if you analyze this waveform, basically you will find that A0 is what? Is 0, isn't it? Because this is a symmetric waveform with along the x-axis, I've got positive and negative exactly the same, so it average out and you don't get any for A0. Out of AN and BN, I will not be doing AN, I will be doing A1 or B1. Out of AN and BN, which one do you think will appear? AN will appear because this is a sinusoidal curve, isn't it? BN will be 0. So let us do only A1. Okay? A1. So what is your A1? 1 by 2 pi, 0 to 2 pi, V theta. So, okay, write down first V theta, sin theta, d theta, isn't it? Okay, so this one I have to split into two parts, isn't it? 0 to pi, V theta, sin theta, d theta, plus pi to 2 pi, everybody agree with me why I need to do that? This is because of the function, isn't it? Because function v theta equal to Vs when theta because of that. Everybody get it? Because the function is not continuous, function is plus Vs during the duration 0 to pi and minus Vs during the duration pi to 2 pi. Okay? So then you replace it here, so you get 0 to pi Vs sin theta d theta minus pi to 2 pi Vs sin theta d theta. Okay, this is minus, so it came minus here. So that gives you 1 by 2 pi. Actually, we can take out Vs, isn't it? So Vs by 2 pi. So first one is sin theta d theta. What is the integral sin theta d theta? Minus cos of theta, 0 to pi. And here again minus cos of theta pi to 2 pi. So if I write it down, Vs by 2 pi, so what I get? Minus cos of pi, minus minus plus cos of 0, minus minus plus cos of 2 pi, and then minus cos of pi, isn't it? Okay? So what do you get? Vs by 2 pi minus cos of pi is what? Cos pi minus 1. So minus minus plus, isn't it? Cos of 0, 1. Cos of 2 pi, 1. Then again minus. So you get 4 Vs by 2 pi. I don't know why that 2 comes. Did I do any mistake somewhere? Actually, this 2 should not come. It should be 4 Vs by pi.
You get the S from both sides.
Hmm? I think we need to check here whether we have this is 2 pi or.
We do that. 2 Vs.
I think this will be.
2 Vs or
I'm not sure here whether it's 1 or 2.
wouldn't that cancel, sir?
Hmm?
Wouldn't that be 2 Vs over pi?
Yeah, no, but I think this 2 will not appear here. It should be 4 Vs by pi. I think it will be this, maybe there is a 2.
How does that work? It's a sine wave.
Yeah, I think there will be a 2 here. Okay. So the formula actually 4 Vs, so An, it will be 4 Vs by n pi. So that's the peak value. Of course, the RMS value will be root 2, you have to divide by root over 2. Yeah, I think in my notes you will find that this one, I think there is a 2.
It's one on pi.
So that will give you one, that 2 will go, so that will give you only pi. Okay, but then when you decide for any other component an, so there will be n coming in the denominator. So now, if you have, this is for the single phase, but what will be the change if the waveform become like that? So for example, your 3-phase waveform, what will be the changes? So the 3-phase waveform you have got like this. So how do you actually calculate the component values? So that's waveform here. Now you are splitting into 6. 0 to 60 degree, you have got Vs by 3. 60 to 120, 2 Vs by 3. Again 120 to 180, Vs by 3. Here minus Vs by 3, minus 2 Vs by 3, minus Vs by 3. So you have to integrate for 6 different regions for the full period.
The notes have it as 2 on T, and it's proposed as a Vs quantity before you convert to the RMS. So that should be 2 on T.
That's a 2, isn't it? Yeah, so this one 2 by T. So that's confirmed, thank you for that one. So this will be all 2, that's why that 2 will not appear in the denominator. So then this 2 is not coming, so effectively there is a 2 here. So that 2 and 2 will cancel, so this 2 will not appear. Yeah, so that's what we will have. Just to bring all these 2, this was actually A0 by 2. This was A0 by 2, so that you have all 2 in the expression. Okay? So if you take only A0, then the problem is here it will be 1 by T, but this is 2 by T. So it's intentionally taken as A0 by 2, so that you have all the 2 here.
now we'll remove the 2 from the 1 or 2 pi, right?
Yeah. So this will be 2. So that gives the peak value, and then if you want RMS value, A RMS, then of course it is AN by root 2. So as you see, because the N appears in the denominator, so that the harmonic value, it decreases with the order of the harmonics, because this N is the order of the harmonic. So if you go very higher harmonic, the magnitude will be less. So PWM technique effectively does that part, that if your harmonics, if we can actually push the harmonics higher, then magnitude of the voltage will be less, and definitely the current, because the current impedance comes into picture, impedance will be even higher, current will be even less.
Is that why they warn you when you're using a really small inductor, a small value inductor, because it means the harmonics will be more intense?
Yeah.
So if you use really big inductors, you avoid the harmonics problem. If you use small, you end up with interference and stuff.
So effectively what happened, so your L is the value, but impedance wise it is omega L. So this omega is 2 pi F. So if you increase your F, then impedance value of the same little inductance can be large. So in terms of the current, because impedance comes in the denominator, so in terms of the current, effect of the inductance will be negligibly, I mean in terms of the current it will be negligibly small because of the effect of the inductance. That's what if you have seen, earlier days there was a, not this one. Earlier days if you have seen the cable of a laptop or the computer, there was some inductor inside the cable. Have you noticed that? Because these days you don't see, because the power supply design has become more mature. But there was inductor, so that inductor ideally it kills the EMI, electromagnetic interference. So when you have got the pulse coming from the external place, if you have an inductor at high frequency, usually the noise is very high frequency. So inductor will actually apply a huge impedance. So that will eliminate the noise coming from the outside source. Okay, so we'll stop here today. I can give you some